I love triangles. Triangles are amazing. They are simple yet so complex. There are so many types of triangles, and they show up in so many theorems and geometric shapes, and their usefulness isn't constrained to just mathematics. One example are video games that use the geometry and simplicity of triangles to create 3D models. These models then become the graphics we see when we play. Though their uses are varied, when you analyze why triangles are useful, it always comes down to their geometrical properties and math. I could talk about the uses and the properties of triangles all day, but today I want to show you a problem that demonstrates one of the reasons why triangles are amazing, why they are magical, or at least why I think so. Let there be 3 points on a single plane. What is the probability that 3 points will be collinear? This problem, like any, can sound hard, but is actually pretty easy once we paraphrase it. To paraphrase, we need to define and understand all the mathy words like collinear, probability, and even plane and point. I'm going to assume that we know what the last two are, but I encourage you to look them up in Wikipedia at least. There is more math regarding points and planes than you would think. Let's start with collinearity. 3 points are collinear if there exists a line that can go through all 3 points. The 3 points shown are collinear, but if we move one of them, they are not collinear anymore. No matter how many lines we draw, none of them can go through all 3 points. If we draw these 3 lines, we get a triangle. More on that later. One of the tricky parts of our problem is that we are dealing with continuous space, meaning we can't divide length into the smallest part. There is always a smaller length we can observe. Our brains don't like this. We work better in discrete systems where there exists the smallest part and everything is made up of these parts. Kind of like building blocks. You can make anything out of them, but the smallest thing is a block. So let's morph our problem into a discrete one and work from there. At this point I would like to mention that even though the solution will be correct, there are more rigorous ways to prove this, taking into regard measure theory and distribution of space and all of that. I'm not going to go into that in this video, because it would take a while, but I would love it if people started discussions about those things in the comments. With that said, let's begin. We can start off by placing 2 points. These 2 points define a line. Now we want to place our 3rd point. At this time we can rephrase our problem from what is the probability of 3 points being collinear to what is the probability of a point being in a predetermined line, the one we just drew. Let's imagine that our plane isn't infinite and continuous, but rather a finite and discrete plane. We can represent our finite plane with a grid where every discrete part, the smallest indivisible part, is actually a point. There are 2 problems that occur when we do this discretization. That's a word, discretization. It is possible to choose 2 points that can't form a proper line on our discrete plane, something that in a continuous plane wouldn't be possible. Also, 2 points can form a line which is quite short, which can complicate our proof. But both of these problems are solved by going back to a continuous system, which, as a part of our proof, we will do, but I still felt the need to address them. Let's say that our grid has an n number of rows and columns. Now we must define the second mathy word, probability. Probability is a number that represents the likelihood of an event happening. It is calculated as a fraction of the number of positive outcomes, the event happening, and the number of all possible outcomes, so the event happening and not happening. From the definition we can see that this is a number between 1 and 0. In our problem, the event is the 3rd point being on the line. When we place our 3rd point, we can place it on any point on the grid. Since there are n times n points on our grid, there are n squared possible outcomes. We don't have to, but we can subtract 2 if we don't want to allow points to be placed on top of other points. Now we can notice that in every column there is exactly 1 point that is on our line. So the number of positive outcomes is n times 1, which is just n. Again, we can subtract 2 for the same reason as before. And there we go. We have our answer. But what do we do with it? We don't have n columns and rows, we have infinite. And what do we do when we calculate something with infinity? We find the limit. This limit is easy to find. We just have to divide both parts of the fraction with n. Break the new fraction apart. N divided by n is 1, n squared divided by n is n, and 2 divided by n, well, we will leave it as is, for now. Now let's let n go to infinity. The 2 divided by infinity gives us 0, which we can just get rid of. Now we have 1 divided by infinity, which is 0, and now we have our answer. The great thing about this proof is that it is quite flexible. Remember the 2 we subtracted from both parts of our fraction? Well, like I said, we don't need to do that. We can allow our third point to be placed on an already existing point, and our answer won't change. In fact, it will be easier to calculate. Also, we don't have to assume our grid has the same number of rows and columns, and the result will stay the same. I'm gonna leave these 2 proofs for you to figure out on your own. They're not that hard. Now let's examine our proof. It's 0. That means when we randomly choose 3 points, we are 0% likely to get 3 collinear points. In other words, we are 100% likely to get a triangle. This is why triangles are magical. They are so incredibly common. We can't choose 3 points without being 100% sure we will make a triangle. There is obviously something wrong here. If the probability is 0, then it shouldn't be possible, right? But it is. I can place them, look. Not just that, but any 3 points I choose from this line are collinear. So either the algebra and calculus we just did has a mistake, spoiler it doesn't, or a result should be interpreted differently. If we look at our original formula and put in actual numbers, we see that as n gets bigger, the probability does get smaller. So our solution makes sense. When doing these calculations, I stumbled upon a few interesting situations. I'd like to go on a tangent about these situations. We will come back to our discussion in a minute. As we look at what happens with our probability as n gets bigger, we can ask, what if n was small? What if it was 1? Well, we get 1, which is 100%. But how? We only have space for 1 point. When we place it, what do we do with the other 2? We can fix this easily by just changing the rules a bit. Our formula doesn't allow for a point to be placed on top of another point. Well, let's change that. Let's say we can place on top of another point, if only there isn't an open space for a new point. That way, we can place all 3 points on top of each other, and we will always get 3 collinear points because we will always get the same point, which we could say it's collinear to itself. If we apply this to a 2x2 grid, we get 0, which makes sense because the third point has room to be placed, but none of the spaces are on the line, and it can't go on the line because it doesn't have room. Okay, now that we've changed our rules a little bit, our tangent is over. Let's go back to our result. Let's go back to our limit. I'm going to change our limit to suit our needs. It will be a small change. Did you see it? I added a plus sign to infinity. This is important because limits can give different answers depending on their signs of infinity. In this case, the answer is still 0, but with something more. A plus sign at the upper right of 0. What does this mean? When we calculate limits, we usually omit these extra signs, especially in engineering, but they actually give us a lot of important information. In this case, our answer is a number that is a tiny bit bigger than 0, but it's not 0. It is the smallest number that is not 0. If for some reason we used negative infinity, we would get a minus instead of a plus, which means our solution would be the biggest negative number, or a number that is just a little bit smaller than 0. So, getting collinear lines isn't impossible, it's just very, very unlikely. How can we make sense of this? Well, the universe is expanding. That's what physicists say, at least. So we can imagine that our plane is also expanding and is always getting bigger, and our probability is constantly getting smaller, but never reaching zero. Every moment that passes, 3 points have a smaller and smaller chance of being on the same line, but they will always have a chance, no matter how small. It's kind of sad, but also kind of hopeful.